Human life is impossible without clean water. So it's hardly surprising that from the very dawn of civilization, people have devoted immeasurable energy, resources, and ingenuity to the development of progressively more sophisticated water supply technologies. Today, in the developed world, our water supply infrastructure has become so effective and so ubiquitous that we're rarely even conscious of it. We simply open the faucet and water flows. But where does this water come from? How is it transported from its source to our homes? How do we know it's safe to drink? Well, as we've seen, only about 0.1% of the Earth's water supply, the surface water and groundwater, is reasonably available for our use. These sources are particularly important to human civilization for two reasons. First, this water has been naturally purified by evaporation from the world's oceans. Second, much of it has been deposited as precipitation significantly above sea level, and therefore it has the elevation necessary to move it to a desired location by gravity alone. So, what are the relative merits of groundwater versus surface water as sources of drinking water? Well, practically from the dawn of civilization, humans have obtained groundwater by tapping into underground aquifers. Recall that an aquifer is a porous stratum of soil or rock in which groundwater collects. Groundwater can be obtained from an aquifer in two ways. One is to dig a well down into the aquifer, allow the water to collect at the bottom, and then lift or pump it up to the surface. The other is to find a spring, a place where an aquifer intercepts the surface, resulting in groundwater flowing freely back to the surface like this. Now, in the ancient world, these groundwater sources were generally preferred over surface water because early civilizations usually dumped their raw sewage into rivers and streams, thus making the surface water unsuitable for human consumption. Today, groundwater sources, particularly wells, remain in widespread use, particularly in rural areas and small municipalities. However, wells generally don't provide an adequate quantity of water for larger urban water systems, and they're unsuitable in regions where the groundwater is subject to pollution or is too far below the surface to be economically extracted. Meanwhile, modern measures for controlling water pollution and more effective water purification technologies have resulted in surface water becoming the principal source for most large-scale water systems today. A water supply system for a large urban population typically includes 6 major elements: a watershed, a raw water collection point, a conduit through which water is transmitted from the collection point to its point of use, a water purification facility, water storage facilities, and a water distribution network. Now, in this lecture, we'll focus on collection and transmission. In the next, we'll look at purification, storage, and distribution. Remember, a watershed is an area of land delineated such that a drop of rainwater falling anywhere on that area eventually drains to the same outlet. Thus, a watershed serves the very useful function of collecting the precipitation falling on a large area of land and then concentrating it in a single watercourse, where it can serve as the source for a water supply system. A given watershed will be adequate as a water supply for a city or town if the quantity of water discharged from the watershed exceeds the current and anticipated future demands of the population being supplied. The demand on a municipal water supply system is typically estimated as about 150 gallons per person per day. No, people don't actually drink that much. Most of this water flows through our dishwashers, washing machines, sinks, toilets, tubs, and showers, at which point it becomes wastewater and is disposed of. Still, whether we drink it or shower with it, 150 gallons per person per day is a lot of water. At this rate, a modest-sized town of 10,000 people consumes 1.5 million gallons per day, or over 500 million gallons per year. Some cities are able to meet this huge demand by drawing water directly from major rivers or lakes. For example, Philadelphia gets its water directly from the Delaware River, and Chicago from Lake Michigan. And by the way, in case you were wondering, Chicago's annual consumption of water constitutes roughly 1/100th% of the water in Lake Michigan, an amount that's easily replenished by the rivers and streams flowing into the lake. Now, in most cases, the quantity or quality of a municipality's local water supply is inadequate, and it must look to a watershed some distance away, often in a less developed region with fewer sources of pollution. And even if a given source provides an adequate quantity of water on an annual basis, seasonal variations in rainfall, and therefore in stream flow, might cause shortfalls at certain times of year. To cope with seasonal variations, the typical urban water supply system uses a dam to create a storage reservoir which receives a variable inflow but holds enough water to provide a steady outflow. No aspect of everyday engineering better exemplifies the grandeur of our civil infrastructure than a dam. So let's talk about dams. A dam is an engineered structure designed to impound water, generally by blocking the flow of a natural watercourse. A dam creates a reservoir and must also control the release of water from that reservoir. Dams are used for water supply, irrigation, flood control, and as we'll discuss later in the course, for the generation of hydroelectric power. But they also create recreation areas, though this is generally a positive side effect rather than the principal purpose of a dam. Many dams serve several of these purposes simultaneously. The iconic Hoover Dam, for example, was originally intended primarily as a source of irrigation water, but it also incorporates a huge hydropower generating facility, supports a wide variety of recreation facilities along the shores of Lake Mead, and it has occasionally mitigated the effects of Colorado River flooding. A dam is generally classified according to two characteristics: its principal construction material, which might be concrete, masonry, soil, or rock, and its structural configuration, either an arch dam or a gravity dam. Let's start with the arch dam, and more fundamentally, with the arch itself. Now, when an arch is used in a bridge or a building, it's generally oriented vertically like this, and the loads that are applied to it are applied vertically as well. An arch carries load primarily in compression, and it can actually carry a tremendous amount of load, provided that two critically important conditions are satisfied. First, it must be made of a material like concrete or stone that's very strong in compression. Second, it must be laterally supported at its base to restrain the ends of the arch's natural tendency to spread outward as it's subjected to a vertical loading. Now, my model here is made of concrete, and it does indeed have appropriate lateral supports represented by these two pieces of wood out at the ends of the arch. So it ought to work reasonably well. Let's give it a test. I'm going to place the arch here on the floor. And if it functions satisfactorily, then it ought to be able to carry my weight without too much difficulty. And indeed it does. However, if we take the same arch and put it on the same supports, but I'm going to flip the support upside down so that those lateral restraints are no longer engaged, now I'm going to apply the same load to the same arch, and the effect is considerably less favorable. Now let's take an identical arch right here, and we'll turn it sideways, and we'll place it in a river valley to create a dam. Now we have an arch dam, and at this point we're ready to fill our reservoir. not bad. Leaks just a bit because I didn't have an opportunity to seal it after I installed it, but structurally this dam works just fine because both the arch and the load that's applied to the arch are now oriented horizontally. The load is hydrostatic pressure. That's the same pressure that's applied to your basement walls by groundwater. Now, as you recall, hydrostatic pressure always acts perpendicular to a submerged surface. Here, the submerged surface of the dam is vertical, so the pressure is applied horizontally. Note also that the lateral support to this arch is provided by the walls of the river valley. And that's why dams like this one, the Glen Canyon Dam in Arizona, are always built in steep valleys with solid rock walls. The other major structural configuration is the gravity dam, which attains its structural load-carrying capacity primarily from its mass. There are two principal types of gravity dams based on whether the construction material is concrete or masonry on one hand, soil or rock on the other. The Dworshak Dam in Idaho is a fine example of a concrete gravity dam. Note that this structure isn't curved, so it doesn't rely on arch action to carry load. So how does it carry load? Well, let's use a diagram of the dam's cross-section to answer this question. Because the dam's upstream face is essentially vertical, the hydrostatic pressure acts horizontally upon it. Assuming that the concrete itself is sufficiently strong, there are really only two ways that this structure can fail. It can either slide horizontally or it can tip about its toe, like this. As long as the base of the dam is keyed into solid bedrock, as you see here, it can't slide. Thus, the design of the dam's cross-section is governed primarily by tipping. Now, the tendency of a force to cause rotation is called a moment. So we say that hydrostatic pressure causes an overturning moment about the toe of the dam. Meanwhile, the dam's weight causes a counterbalancing moment about the same point. As long as the counterbalancing moment is greater than the overturning moment, the dam won't tip. Mathematically, the counterbalancing moment is equal to the dam's weight times this horizontal distance from the toe to the dam's center of gravity. Thus, to prevent the tipping failure of a gravity dam, it must have both adequate weight and adequate width. And that's why concrete gravity dams like the Grand Coulee Dam shown here are always massive and wide. Monumental concrete dams like this one are impressive structures indeed. Yet, at the opposite end of the technological spectrum, we'll find gravity dams that are, in many ways, even more fascinating. These structures are made of the least sophisticated structural materials available, soil and rock, but involve surprisingly sophisticated engineering. They're called Earth Dam and the Rockfill Dam. Here's a particularly impressive example, the Anderson Ranch Dam in Idaho, though many more modest examples abound. Indeed, the Earth Dam is the most common type used in support of municipal water supply systems, so it's particularly relevant to this lecture. Let's build a model. Here's a valley with a stream running through it. We'll begin construction by installing the outlet works. That's a conduit and associated equipment that will eventually be used to control the release of water from the reservoir. I'm going to place it right into the middle of the river valley. And once it's in position, this allows the stream to be diverted through the outlet works so the water won't accumulate in the valley while we're building the dam. Now here, in the center, at the future location of the base of the dam, we would clear away all the topsoil until we've reached bedrock or a strong stratum of underlying soil. On this solid foundation, we'll build the core of the dam using this trapezoidal mass of clay. Now, clay is an extremely fine-grained soil formed from the weathering of silicate-bearing rocks. It has a very unique microstructure, which makes it highly cohesive. That means that it's capable of holding its shape without crumbling, and also highly impervious to water, a particularly advantageous property for the core of a dam. Take a minute to make sure our clay core is properly sealed. around the edges of the valley, and most importantly, at its foundation down here. And we're ready for the next stage of construction. Now, a dam can't be made entirely of clay because this material would be very easily eroded, and it doesn't have the mass necessary to resist the hydrostatic pressure that the completed dam will be experiencing. Thus, we need to cover both faces of the core with gently sloped layers of compacted fill. If this fill is soil, then the structure is called an earth dam. If it's primarily rock, then we call it a rock fill dam. In this case, let's build an earth dam. I'm going to take some soil, deposit it on what we'll call the upstream side because the stream is flowing from your right to left. And we're going to fill that region in and completely cover over the upstream face of our clay core. And I'm going to do the same on the downstream face with another layer of soil. We're going to smooth that out and compact it so we have a nice, clean, smooth face for the formation of the dam. And I'll do the same on the downstream face. Of course, on the upstream face, that compacted soil is likely to wear away with the action of water once the reservoir is filled. So we'll also armor the upstream face with a layer of heavy stone. And that heavy stone will protect the upstream face from erosion and from any potential problems with ice accumulation or objects floating in the reservoir that might damage the dam through collision or contact with the upstream face. Whether we're talking about soil or rock fill, all of these layers add both strength and mass to the structure and therefore improve its overall stability. In addition to the armoring on the upstream face, it's also common practice to plant vegetation on the downstream face in order to further stabilize the soil and prevent erosion. In this photo of the Saint-Cassien Dam in France, you can clearly see these protective layers, stone on the upstream side and vegetation on the downstream side. Also notice this elaborate concrete chute along the side of the dam. This structure is called a spillway, and it's used for the controlled release of surplus water to prevent the dam from being overtopped. This is a particularly important feature of earth and rockfill dams, where overtopping can very quickly erode the protective fill on the dam's downstream side and lead to a catastrophic collapse. For this reason, spillways are very carefully designed using the science of hydraulics to guide their size and shape. The graceful curved shape of this elaborate concrete spillway on the otherwise simple Anderson Ranch Rockfill Dam is specially configured to minimize turbulence, which could damage the channel in a major flood. The pool at the bottom, called a stilling basin, is designed to dissipate the energy of that high-velocity stream plunging down the spillway to prevent scouring that might undermine the foundation at the toe of the dam. Now note that my model also incorporates a spillway here along the valley wall at the edge of the dam. With the stream running, I will now close off the outlet works so that we can fill our reservoir. So here's the normal configuration of our dam and reservoir. But if heavy rains come along and cause flooding, we can see how the excess water is channeled down through the spillway and into the outlet channel before it can overtop the remainder of the dam and cause a failure. Now, in contrast with the spillway's use in emergency or extraordinary situations, the outlet works down here are used to control the routine release of water from the reservoir to fulfill the dam's intended purpose. For a water supply dam, gates or valves on this conduit are used to regulate the flow into a pipeline, aqueduct, or canal. For a flood control dam, they control the reservoir elevation by regulating downstream flow. For a hydroelectric power facility, they regulate the flow to the turbines. Now, so far our dam looks reasonably dry, but it's important to recognize that all earth dams experience some seepage. So if we wait around long enough, we'll surely see some water accumulating here on the downstream side. Accommodating this seepage is an integral aspect of dam design. This diagram shows a typical cross-section of an earth dam. Here's the impervious clay core, and here are those outer layers of compacted fill. In between is a filter, a seam of specially selected permeable soil that captures seepage and directs it safely out of the dam, while retaining the fine-grained clay core in its proper position. The most obvious difference between an earth gravity dam and a concrete gravity dam is the very shallow slope of the earth dam's outer faces. As you might expect, this feature enhances the stability of the earth embankment. Shallow slopes are much less susceptible to landslides than steep ones, but it also has a very beneficial effect on the dam's loading. Recall that hydrostatic pressure always acts perpendicular to the surface of a submerged body. Thus, the pressure on the upstream face of an earth dam looks like this. Its orientation is now more downward than horizontal, and so it actually compresses and further stabilizes the earth fill, while also decreasing the horizontal force on the dam and increasing the friction between the bottom of the dam and its foundation. Well, now that you've seen how various types of dams work, you're probably wondering how engineers decide which type to use in a given situation. In general terms, concrete dams are preferable to earth and rock-fill dams where the reservoir needs to be very deep, a situation that's usually dictated by the topography of the valley, the required water storage capacity, or the need to generate hydroelectric power. Topography also has a major influence on a dam's structural configuration. A deep V-shaped valley with a solid rock wall is ideal for an arch dam. A somewhat wider valley with high walls would favor a concrete or rock-filled gravity dam. A broad, low valley would generally call for an earth dam, particularly if the valley floor were covered with a deep layer of alluvial soil, because earth dams don't necessarily have to be constructed on bedrock as concrete dams do. Returning to our broader examination of water supply, we've now discussed the watershed, the dam that impounds runoff collected by the watershed, and the outlet works, which control the flow of water from the reservoir into an aqueduct. An aqueduct is a conduit used to transport water from its source to its point of use, typically a city or town. The water channel can use any of four basic configurations depending primarily on the terrain being traversed. And we can explore all four configurations by examining a single real-world system, the Catskill Aqueduct, a 92-mile conduit that carries about 40% of New York City's water supply from an upstate watershed down to the city. Built between 1907 and 1917, the Catskill Aqueduct draws its water from a 123 billion gallon reservoir formed by a 4,650-foot dam across the Esopus Creek near Olive Bridge, New York. Driven entirely by gravity, up to 600 million gallons of water flow through this aqueduct every day. It crosses 5 major geological regions and the mighty Hudson River, while surrendering less than 300 feet of elevation over its entire 92-mile length. The conduit ends at the 900 million gallon Hillview Reservoir in Yonkers, New York, where its water is fed into the city's equally impressive water distribution network. This receiving reservoir serves two functions. It provides a reserve of several days' water supply in case the aqueduct needs to be temporarily shut down for maintenance or repair, and it also accommodates the continuously changing differences between the aqueduct's relatively steady inflow and the city's hour-by-hour variations in demand, with purposeful consideration of the need to supply a huge quantity of water quickly in the event of a large fire. Now, this model illustrates the four distinctly different channel configurations constituting the Catskill Aqueduct. Up here we see the dam and the reservoir that is formed by that dam. And what I'm going to do is fill the reservoir, and with the outlet works open, we'll see how water is transmitted through the 4 different segments of the Catskill structure. The first channel configuration that we're going to talk about in the Catskill Aqueduct is called cut and cover, constituting about 55 miles or 60% of the aqueduct's total length. This segment of my model represents a cut and cover segment. This drawing shows the standard cross-section used for all cut and cover segments in the Catskill system. It was built by cutting a shallow trench into the soil and then casting this horseshoe-shaped concrete tube 17.5 feet wide and 17 feet tall, and then covering the tube with a soil embankment. Longitudinally, this channel is constructed on a constant downhill slope of 1 foot of elevation for every mile of length, following the contours of the earth as necessary to maintain this gradient. The finished product shown here might easily be mistaken for an elevated hiking trail. But as you're walking along that path, it's worth remembering that 7,000 gallons of water are flowing beneath your feet every second. Don't you just love the sound of flowing water? So the next 15% of the Catskill Aqueduct consists of something called a grade tunnel, which is designed to carry the channel through mountains of solid rock at 23 different locations along the route. The grade tunnel in my model is represented by this section here. Now, as shown in this diagram, the irregular tunnel opening was reinforced with a concrete liner using essentially the same horseshoe shape that we saw in the cut and cover channel, though somewhat narrower to reduce the amount of required rock excavation. To keep this narrower channel from constricting the flow, its slope was doubled from 1 foot per mile to 2 feet per mile. And note in my model that both of those features are present. In the grade tunnel segment of the model, you see that the channel height is reduced just a little bit, and the slope is increased just a bit as well. This increased gradient allows the water to flow faster, thus compensating for the reduction in channel size at the grade tunnel locations. Now, in the science of hydraulics, the movement of water in both cut and cover conduits and grade tunnels is classified as open channel flow. This might seem odd because both of these channel configurations are fully enclosed in the Catskill Aqueduct. But the technical definition of open channel flow requires only that the moving fluid has a free surface. In other words, the conduit flows only partially full, with the water at the surface at atmospheric pressure. To maintain its flow, an open channel requires a steady downhill gradient, just as we've seen with the cut and cover and grade tunnel segments of the Catskill Aqueduct. The concrete covers over these channels don't have any effect on the flow within. Rather, they just serve to protect the water from evaporation and contamination. In contrast, the remaining 2 configurations used in the Catskill Aqueduct are characterized by true pipe flow, with their conduits flowing full and under pressure, and thus with no requirement for the channel to assume a continuous downhill gradient. One of these 2 pipe flow segments is the inverted siphon, represented here in my model. Its purpose is to transmit water across a valley with a pipeline placed at ground level. Note that water will flow through an inverted siphon even though a portion of its journey is uphill, as long as the upstream water level is higher than the downstream water level. This elevation difference supplies the pressure that keeps the water moving through the siphon. The Catskill has 19 of these structures, constituting about 7% of the aqueduct's total length. To resist their substantial internal pressure, the Catskill siphon pipes were constructed of huge steel cylinders, each 11 feet in diameter and 9.5 feet long, riveted together, lined with mortar on the inside, encased in concrete on the outside, and then covered with a protective layer of soil. And Impressive as these structures are, they pale in comparison with the fourth channel configuration used in the Catskill system, the pressure tunnel. These, represented by this final segment in my model, total 17 miles or 18% of the aqueduct's total length. Their purpose is to carry water across particularly deep valleys and deep rivers, locations where a surface level siphon simply wouldn't be feasible. By far, the most impressive of the Catskill pressure tunnels is the one that passes underneath the Hudson River at a place called Breakneck Ridge. Here we see the profile of this astonishing 6-mile system. With water entering from a cut and covered channel several miles from the river and then plunging through a series of vertical and horizontal shafts, bottoming out 1,140 feet below the surface of the Hudson, and then ascending to the eastern shore. All of these shafts are 14-foot diameter concrete-lined conduits. No doubt, you recognize that a pressure tunnel works in exactly the same way as an inverted siphon. The only difference between them is that the pressure tunnel is bored through bedrock, while the inverted siphon is placed on the ground surface of the valley. The extraordinary 1,100-foot depth of the Hudson River pressure tunnel was required because the riverbed at this location is covered with nearly 800 feet of loose alluvial material that wouldn't have allowed for a watertight tunnel. This depth was also dictated by the need for the weight of the rock above the tunnel to offset the extremely high internal pressure of the water flowing through the conduit. Interestingly, these two segments of vertical shaft were essential for access to the pressure tunnel during construction, but then they had to be sealed up to preserve the internal pressure that makes a siphon system work. The downtake shaft on the west bank was sealed permanently with a 50-foot plug of concrete, but the uptake shaft on the east bank was sealed with a 46-ton steel dome that can actually be removed for maintenance access. The steel dome is housed inside this beautiful, if somewhat time-worn, stone building, providing the only visible indicator that the Hudson Pressure Tunnel, one of the world's great civil engineering achievements, lies hidden 1,100 feet below. In this course on everyday engineering, an extraordinary engineered system like the Catskill Aqueduct might seem a bit out of place. Certainly, its scope and complexity are not entirely representative of the smaller, simpler water supply systems used by most municipalities. Yet each of these smaller systems applies the same basic hydraulic concepts as the Catskill, and each employs some of the Catskill's technologies, albeit in simpler form. More important, the Catskill Aqueduct stands as a powerful reminder that sometimes everyday engineering is anything but mundane. Thus far in our exploration of water supply, we've examined the technologies used to collect raw water from a watershed and then transport it to the municipality where it will be used, not only for drinking, but also for cooking, personal hygiene, washing clothes and dishes, circulating heat through homes, watering lawns, a wide array of commercial and industrial purposes as well. But regardless of whether it's been delivered by an aqueduct, pumped from a well, or drawn from a nearby lake, this is still raw water, and as the name implies, it isn't ready for human consumption just yet. Raw water from certain kinds of sources, an upland spring or a deep groundwater well, for example, might be reasonably pure and potable, that is, safe for drinking. But most raw water, particularly surface water, is loaded with contaminants, some of which can be extremely hazardous to human health. These contaminants include microorganisms such as viruses, bacteria, and protozoa, dissolved salts and metals like sodium, calcium, and magnesium, other inorganic chemicals like arsenic, asbestos, cadmium, lead, mercury, nitrates, Organic chemical compounds like benzene, dioxin, and polychlorinated biphenyls, or PCBs, and even radioactive uranium and radium. Some of this contamination is beyond human control. For example, one of those nasty microorganisms, the Legionella bacteria, which causes Legionnaire's disease, is found naturally in the environment. Arsenic, lead, mercury, and radioactive particles can originate from the erosion of natural deposits. Calcium and magnesium are dissolved into groundwater when it percolates through geologic formations of limestone, chalk, or dolomite. And by the way, this process is the cause of so-called hard water. But most contamination of raw water is caused by human activity in the watershed. Dangerous pathogens like Cryptosporidium and Giardia originate from human and animal feces. Many chemical contaminants are discharged from industrial facilities, petroleum refineries, steel mills, chemical plants, pulp mills, and mines. Cadmium enters our water from the corrosion of galvanized steel pipes and improper disposal of batteries and paints. Nitrates come primarily from fertilizers, carried from agricultural land and residential yards by storm runoff. Much organic chemical contamination originates from the use of herbicides and insecticides, again transported into our water supply by storm runoff. Clearly then, water quality can be improved to some extent by controlling the human causes of contamination, by designing effective sewage treatment and stormwater management systems, constructing landfills with proper containment, minimizing industrial pollution, using agricultural methods that control erosion and reduce excess application of fertilizers and pesticides, refraining from using these chemicals in our own yards, and promoting the responsible handling and disposal of fuel, motor oil, batteries, and other hazardous materials. When implemented comprehensively and conscientiously, these sorts of measures can significantly reduce the contamination of our raw water sources, but they can't eliminate it. Agriculture and manufacturing are integral to our prosperity and quality of life. Many of these industries' unhealthy byproducts are essentially inseparable from the benefits that we enjoy and are very difficult to dispose of in an effective, environmentally responsible manner. Thus, some level of contamination is practically inevitable, and municipal water supply systems always require some level of treatment. In the U.S., under the provisions of the Safe Drinking Water Act of 1974, the Environmental Protection Agency has primary responsibility for regulating water quality to ensure public safety. The EPA fulfills this responsibility by setting and enforcing maximum permissible levels for over 80 possible contaminants. EPA rules also specify in general terms the treatment processes required of all public water systems, though individual municipalities do have the flexibility to adapt these processes to their own needs. This is the business of environmental engineers, the unsung heroes who design, build, and operate water treatment facilities and processes consistent with a given community's needs and available water resources. In this endeavor, the engineers are greatly aided by environmental scientists and chemists who develop the protocols and technologies for testing water to determine contamination concentrations accurately. So let's talk about water treatment. And while our primary focus will be on your local water treatment plant, it's important to recognize that some aspects of water purification begin before the raw water ever reaches this facility. When water is impounded in a reservoir or lake, a number of water quality problems may result. The first is the growth of algae and aquatic plants, which feed on fertilizers that are washed into the reservoir by storm runoff. This satellite photo shows a huge algae bloom in Lake Erie, and its proximity to the shoreline suggests an intimate connection to runoff from the lakeshore. Some algae and plants are toxic, but most are just a nuisance. They give the water an unpleasant taste and may foul pipelines and pumps. The best defense against algae is to deny it food by using storm runoff management to keep fertilizers out of the reservoir. If this approach isn't feasible, then the algae can be removed mechanically using a device like this algae harvester, or they can be killed by treating the water with a chemical, copper sulfate. But this chemical must be used with some caution. Not only can copper sulfate be toxic to fish if it's used in excessively high concentrations, it can also exacerbate another problem that's often encountered in reservoir management. That problem is called anoxia, the depletion of dissolved oxygen near the bottom of a body of water. Anoxia can occur naturally as a result of inadequate water circulation. But if copper sulfate treatments kill too much algae too fast, the loss of dissolved oxygen will be greatly accelerated by the oxidation of all this rotting organic material. Anoxia kills fish. They actually suffocate for lack of oxygen. And it also encourages the growth of anaerobic bacteria, which give the water a foul smell. The cure for anoxia is aeration, which restores oxygen to the water. Now, a century ago, this process was accomplished by installing elaborate fountains near the outlet works of a reservoir, just like this one at the Ashokan Reservoir. Today, however, environmental engineers use a technique that's less splashy, but more effective. An air compressor on shore forces air through a pipe to a fixture located at the bottom of the reservoir. This device works just like the aerator in a home aquarium, sending a continuous stream of bubbles up to the surface. These bubbles add oxygen to the water in the immediate vicinity of the aerator, but more importantly, the upward stream sets up a circulation pattern that effectively turns the lake upside down, drawing the oxygen-starved water up to the surface where it can be replenished naturally. Now, onward to the water treatment plant, which uses an integrated series of mechanical and chemical processes to perform three basic functions: clarification, filtration, and disinfection. Let's use this process diagram to explore step by step how these functions are performed. As raw water is pumped from a lake, river, or receiving reservoir into the treatment plant, it passes through a series of progressively finer gratings and screens to remove trash, leaves, aquatic weeds, and critters like fish, tadpoles, and zebra mussels, which have no business swimming around in our drinking water. The water then enters a mixing basin where a chemical coagulant is added and vigorously mixed. The purpose of the coagulant is to neutralize the electrical charges that cause suspended particles in the water to repel each other. The coagulant causes these particles to cling together, forming progressively larger clumps of impurities called flocks. This process, called flocculation, concludes when the flocks get so heavy that they settle down to the bottom of the basin. Now let's see how this clarification process works. Here's a container of some very dirty water that I obtained from a local swamp. I guarantee you, no water this dirty is ever going to be admitted into a water treatment facility. But I've used it here really just to exaggerate the effect of that chemical coagulant that I'm about to demonstrate. I'm going to mix into this water a substance called alum, a common chemical coagulant that's often used for cleaning swimming pools. I'll add the alum, I'll mix it vigorously to dissolve those crystals into the water. We'll see how it works. Now, in the treatment plant, this mixture of raw water and coagulant now passes from the mixing basin into a flocculation chamber where the coagulant does its magic. Here, the water is gently mixed so the fine particles will continue to encounter each other, but without breaking up the ever-growing flocks. With flocculation underway, the stream passes into a sedimentation basin where the water is stilled and the flocks sink to the bottom. This accumulated sludge is periodically raked out, dried, and disposed of in a landfill. Now, it generally takes 30 minutes to an hour for the flocculation and sedimentation processes to play out. So we won't really start to see significant results in this experiment until the end of the lecture. But about 45 minutes ago, I added the same amount of alum to a sample of equally dirty water, and here it is now. It certainly isn't perfectly clean, but I think you can see why this first phase of water treatment is called clarification. Back at the treatment plant, the clarified water is now pumped through a filter, typically composed of horizontal layers of gravel, sand, and anthracite coal. As the water passes through this filter, any particulate matter that didn't settle out during clarification is captured in the tiny voids between the sand grains. The coal serves as a source of carbon, which is particularly effective at capturing volatile organic chemicals and removing them from the water. With filtration complete, the water is disinfected, usually by mixing in a small quantity of dissolved chlorine, which kills any bacteria or viruses that might have survived clarification and filtration. Alternative methods of disinfection include exposing the water to ultraviolet light or ozone. Both of these methods are also quite effective at killing pathogens. Finally, the purified water passes into a holding tank, which gives the chlorine more time for disinfection while also providing a reservoir for smoothing out fluctuations in demand. At this point, the water treatment process is complete and the finished water enters the local distribution system. But before we examine water distribution, I need to say a few words about a different type of water treatment process, a process that converts seawater into drinking water for roughly 300 million people around the globe. This process, called desalination, has been around for a long time, but it's undergoing a major surge in popularity today as a result of recent technological advances. The most important of these is a technology called reverse osmosis, which removes salt from seawater by forcing it through a membrane under pressure. These sorts of improved technologies have cut the cost of desalination in half over the past decade. Nonetheless, desalination is still significantly more energy intensive and therefore more expensive than treating surface water or groundwater. And its economic viability is further constrained by the fact that seawater is always obtained at a low elevation, a seacoast, and thus must always be pumped to a higher elevation and transported inland for consumption. Nonetheless, there are places in the world, like Oman, shown here, where desalinated seawater is practically the only reliable water source available to entire populations. Another such place is Israel, where the recent construction of several high-capacity desalination plants have provided this drought-ridden country with the capacity to produce surplus drinking water for the first time in its history. As the technology continues to improve, we can expect to see more of this trend. For example, the cities of Los Angeles and San Diego are currently considering the construction of desalination plants as a means of addressing their persistent water supply challenges. Now, back to our local water distribution system. The single most important characteristic of this system, the characteristic that distinguishes it from both storm drainage and sanitary sewer systems, is that water distribution operates under pressure. To use the hydraulics terminology I introduced in the last lecture, water distribution is based on pipe flow rather than open channel flow principles. The pressure that makes a pipe flow system work can be provided by gravity, but only in the rare circumstance where the water treatment facility is located at a higher elevation than every consumer served by the distribution system. In all other cases, the pressure must be supplied by one or more pumping stations, often housed in a nondescript building like this one, and using one or more electric pumps to propel water from the treatment plant into the distribution network. The network is composed of large pipes called water mains, smaller pipes called service lines, connectors, valves, fire hydrants, and most importantly, an intermediate storage facility, which greatly enhances both the efficiency and robustness of this system. Let's see how this ingenious system works. This container of water represents the finished water holding tank at a water treatment facility. I'm going to use this electric pump to represent the pumping station, and as you can see, I'm using plastic tubing to represent the water main and the service lines branching out from the water mains to individual residences. And here is our intermediate storage facility, typically a water tower located on high ground close to the population it serves. Now let's say that it's midnight. Most of the town is asleep, so there's very little demand for water. Nonetheless, the pump is running, and because all of these faucets and shower heads are closed, Most of the water is being pumped up into the water tower through this central conduit at the base of the tower. By the time morning arrives, the tank is quite full, and that's good, because within a 2 or 3 hour period, practically everyone in town will open a faucet, take a shower, shave, or make a pot of coffee, resulting in significant additional demand for water. The pump now can't keep up with a sudden surge in demand. That's okay, because as the pressure in the water main drops, water automatically begins flowing back into the pipe network. In effect, the water tower is now providing additional pressure to help the pump meet peak demand. Now, later in the morning, people head off to work and the demand drops off considerably. Perhaps even enough for the water tower to begin refilling, but only till dinner time, when demand peaks again and the water tower once again supplements the pump. Finally, night falls and the cycle begins again. Now, 2 aspects of this ingenious system are worth emphasizing. First, it's highly efficient, because without that water tower, a much larger pump, or perhaps several larger pumps, would be required to meet the peak demand. Second, the system is robust, because the tower will continue to supply water even if a power failure shuts down the electric pumps. I should add that most municipal water systems are required by law to have backup power systems, typically diesel or gas generators, for their pumping stations. But backup generators won't necessarily kick in instantaneously after a power outage, so the water tower is critical for providing continuity of supply. This is particularly important because water distribution systems supply fire hydrants as well as residences and businesses. And the emergency that knocks out electrical power might be a fire. That's why an intermediate storage facility is usually designed to have enough capacity to supply the municipality for at least 1 full day, plus the additional water required to fight a fire. You know, I have occasionally heard it said that water towers are ugly, that they're an obtrusive, utilitarian blight on our landscape. I beg to differ. The water tower is a beautiful icon of our civil infrastructure. A simple, robust technology that clearly manifests the laws of physics underlying its design, that makes life incalculably better for the many thousands of people living in its shadow, that almost always tells us something about the era and the community in which it was built. The water tower can be a humble piece of Americana or the symbol of a great city. It can be futuristic or traditional, high style or brutally simple. It can be whimsical or serious, architecturally distinctive, or even majestic. The water tower can be an expression of civic pride and patriotism, evocative of history and culture, sometimes demanding to be seen, sometimes preferring to remain hidden, often doing double duty as a high perch for cellular phone antennas, occasionally just bidding us to have a nice day. You know, if I accomplish nothing else in this course, I hope I can convince you that the humble water tower is a piece of everyday technology that's worth noticing and worth celebrating. Now, back to the water distribution network, which is somewhat less colorful than the water tower, but no less important. Water mains are large pipes, generally at least 6 inches in diameter, but often much larger, sometimes made of PVC plastic or steel, but most often made of iron, which resists corrosion better than steel. And corrosion is the most common cause of those water main breaks you're always hearing about on the evening news. These pipes are almost always located underground to protect them against freezing. As such, the depth varies from 3 to 4 feet in the southern US to 6 to 8 feet in the northern states to 12 to 15 feet in Alaska. As this computer model illustrates, water mains generally follow public streets because the municipality already owns the right-of-way here. Storm drains and sanitary sewers also follow the public streets, and because all 3 of these systems have distinctly different points of origin and distinctly different destinations, there's a great potential for them to interfere with each other. When such conflicts occur, it's always the water main that dips beneath or bends around the other two systems. Can you guess why? Hopefully you recall that storm drains and sanitary sewers operate under the principle of open channel flow, and so their channels must be constructed on a steady downhill gradient, without exception. Conversely, the water distribution system is the only one of the three that operates under pressure. Thus, water mains can change gradient and direction with no problem, even flowing uphill when necessary to avoid a conflict with a storm drain or sewer. For this same reason, water mains typically don't use the river-like topology we saw in storm drainage systems, with many small tributaries flowing into progressively smaller numbers of larger streams. Ideally, water mains are arranged in interconnected loops, which can also be visualized as a grid pattern. Dead-end branch lines are used only where loops are impossible, for example, at cul-de-sacs. So why are loops better than branches? Well, suppose the water main failed at this location. It would be easy to isolate this small section of the main and make the necessary repairs, disrupting water supply to only a very limited number of homes thanks to this looped configuration. Water can flow through a main in either direction, and because the system is pressurized, the water will always find its own path around a closed segment, like this. Of course, to fully realize this advantage, the distribution network must have lots of shutoff valves that can be used to isolate any segment of the system for maintenance and repair. And as this diagram indicates, modern water systems do include lots of valves. When you see one of these metal covers at street level, there's usually a shutoff valve a few feet below. On the other hand, with a branched topology, a failure here would cause many more homes to lose their water supply until the repair was completed. This situation is sufficiently problematic that in many municipalities, the developer is required to provide an easement, allowing the utility company to run a water main across private property to the next cul-de-sac, turning two branches into a loop like this. Now, the greatest challenge in designing a water distribution network is maintaining an appropriate level of pressure throughout the system. Most systems operate with water mains pressurized between 40 and 60 pounds per square inch, or PSI. As a point of comparison, the pressure in your car tires is about 30 PSI. At pressures above 80 PSI, residential plumbing fixtures and pipe joints will start leaking. And below 20 PSI, the flow of water to a third-story shower head will be little more than a dribble. If the region served by the water distribution system has large changes in elevation, the system must typically be divided into several pressure zones, interconnected with special pressure regulating valves. Perhaps the greatest challenge in regulating water pressure is in a high-rise building, where heavy-duty pumps are required to move the water from ground level up to the highest floors. In general, 1 PSI of pressure will lift water 2.3 feet. Thus, One World Trade Center would require over 500 PSI at ground level to move water all the way up to its highest occupied floor at 1,268 feet. Of course, this would cause the pressure at ground level to be impractically high. Thus, most tall buildings use a series of pumps placed at regular intervals from bottom to top. And even then, pressure relief valves must be used for the water distribution lines in the immediate vicinity of the pumps. Now, thus far, we've been looking at the public component of the water distribution system: the water treatment plant, intermediate storage facility, and water mains. But there's a private component too. And it begins underneath a street in front of your home, where a copper or plastic service line branches off from the main and conveys a stream of potable water into your plumbing system. At your property line is a curb valve, which can be used to cut off your entire water supply from outside your home, either for maintenance or if you don't pay your water bill. Beyond the curb valve, the service line enters your home through a hole in the foundation wall or floor slab. Just inside is your water meter and an interior shutoff valve. This is the one you'll want to close to keep your basement from flooding when a pipe bursts. From here, a separate pipe branches off of the main service line to supply the hot water heater. From this point forward, the hot and cold water lines run parallel to each other throughout the building, supplying sinks, tubs, and showers, while the cold water line also individually supplies toilets, exterior spigots, and perhaps an ice maker in your refrigerator. Throughout this network, whenever you open a faucet, turn on a shower, use a washing machine, or flush a toilet, water flows freely because of the combined effects of a distant pumping station and a water tower, which supply the pressure that makes the system work. But pressure is a double-edged sword. Water that's flowing through a pipe under pressure has considerable momentum. If the flow is shut off suddenly, by quickly closing a faucet, for example, the resulting shock, called water hammer, can damage pipe joints and fixtures. To prevent water hammer, water supply lines are fitted with these air-filled expansion chambers, which effectively absorb the shock. Well, you open a faucet and clear, clean water flows. Let's close today's lecture by reflecting on where that stream of water originated, as surface runoff in a distant watershed, impounded as raw water in a reservoir created by a dam, collected and transported through an aqueduct to a water treatment plant, clarified, filtered, and disinfected through an integrated series of physical and chemical processes, and then delivered to your kitchen sink at just the right pressure by a robust, redundant network of pumps, pipes, valves, and water towers. This is the epitome of everyday engineering, an immense, integrated, multi-dimensional technological system of which we're largely unaware, delivering this precious, life-sustaining substance on demand. But in a broader sense, we've only really seen half of this system. If our water distribution system supplies 150 gallons per person per day, what happens to all this stuff after we've used it? Next, we'll answer this question as we explore the most aromatic aspect of everyday engineering, wastewater disposal and treatment.